Welcome to the presentation of our paper Dynamic Pattern Matching with Python for the Dynamic Language Symposium 2020. My name is Tobias Kohn and I'm going to present to you key aspects of our paper tonight. Of course, you will find a much more detailed exposition of how we implemented these features in Python in the actual paper. Also note that there's an accompanying Python enhancement proposal with further specifics on the implementation side. You would usually think of pattern matching as a tool of statically typed and functional languages. So we set out to investigate how to integrate and adapt this feature to the dynamic programming language Python. In this presentation, we will first briefly look at what is pattern matching in general, and then how to account for dynamic objects. Other aspects of this can be found in the actual paper. The objective of pattern matching, as we understand it, is to filter and extract data that is organized in tree structures. That is to say, that we want to impose some structural constraints on the data that our code is going to work with, and then automatically extract relevant bits of information from that data and further process those. Let's start with a simple example. The expression here is just a product of a number and a variable. We can express this in the abstract syntax tree with a binary operator node containing three further nodes, one for the number, 123, one for the start rate of a multiplication, and one for the name n, representing the variable. You can write this as a tagged tuple, or object if you will, where binob is a tag, or class, followed by an actual tuple containing the three relevant elements that make up this binary operator node. Now, for pattern matching, we assume that we are given some data that is like a tree structure, such as the binary operator node you have just seen. And we then specify a template or pattern on the structure of the data, how we expect it to be. In this case, the binary operator node on the top actually matches the template or pattern below, so we can assign the number 123 to the first slot and the name n to the third slot, allowing us to extract these two elements and store them in the variables x and y. In reality, of course, we want to account for more than one possible structure that our data might have. In this case, for instance, we account for an unary operator node with two elements, or a binary operator node for the multiplication as we saw before. In the first case, we just extract one bit of information, and in the second case, we actually extract two bits, and then further process them. In Python code, we express this through a match statement, where the keyword match is followed by the data subject. This is the data that we are given, the input that we want to analyze and extract information from. This is then followed by one or several case clauses, each of them with their own pattern that tells us what kind of structure we are expecting in this particular case and what kind of information we want to extract from them. Note that each case clause has its own process code to then further handle the data that is extracted. Here's a very simple example, a simplify function that expects an abstract syntax tree expression and then allows for two possible structures to further simplify them. In the first case, we have a unary operator node that contains yet another unary operator node. This represents a minus some expression. In that case, we can just cancel the minus and return the simplification of the expression in the center. In the second case, we have a binary operator node that represents a multiplication of an expression with the number 1. In that case, we might decide that we can just throw away the multiplication and return the simplification of the expression on the left. In reality, of course, this will have many more case clauses to account for even more structural variety. But this should actually already convey the basic idea and feel of pattern matching in Python. A different way of how to look at pattern matching is to think of pattern matching, or think of a pattern as a constructor for a tree structure, such as a tuple, say, where in this case, on the left-hand side, we have a constructor for a binary operator node, where the first item is a number 1, the second one is the star operator. However, the third one is a hole labeled y, so we are missing some bit of information. And we want that the object yielded by this constructor equals a subject given. So we want to find some value for y that we can plug in here so that the constructor on the left yields the same object as the subject we are given. In other words, given a pattern P with variables x, y and so on and a subject s, find a substitution that assigns a value to each of the variables in the pattern such that if we replace the respective variables with their values in the pattern, we get back the subject. So here comes the interesting part. As soon as we move from tagged tuples to actual objects, there are two major challenges that we have to address. On the one hand, in contrast to a tuple, an object does not store its elements sequentially, but refers to them by named attributes or fields. On the other hand, a class might not fully determine or describe the structure of an object. Think, for instance, of an object that's an instance of a subclass. Or in Python, since it is a dynamic language, we can actually add or remove attributes to an object at any given time, which is not reflected by the class of the object. This means if we return to this picture of having this tree structure binom that we then assign to the slots of a pattern, we actually have to account for the fact that the three nodes number, star and name are not referred to in actuality by position, but rather by name. So the number node is stored in an attribute left, the star in an attribute up, and the name n in an attribute right in this case. But there's nothing telling us that this is the one and correct order of these three named attributes. So we might find that in actuality up is the first of these attributes and left and right are the second and third respectively. Even worse, there might be an additional attribute for the line number where the original expression was found in. So the question really arises, how do we map the object to the pattern? How do we assign one of these attributes to the respective slots in the template or pattern? And there are two possible answers to this. The first answer is to label the slots in the pattern themselves. So in this case, we say that in the binom pattern, the first slot refers to the attribute left, the second slot to the attribute up, and the third slot to the attribute right. In Python code, we write this like named arguments. So the unary operator pattern on the top here, explicitly says that the minus sign refers to the op attribute and the item attribute should be extracted and stored in the variable x, for instance. The second answer to the challenge is to say that we want the binom class to actually act as a mapping or function that determines which attributes go to which of the slots of the subsequent pattern. So we think of this binom class as a function pi that takes an object and either returns a tuple or a marker to say that there's no possible way of interpreting the subject as a binom structure. We can either do this through a passive mapping, which is to say that we just have a static field match args, a tuple of names that tell us the order of the attributes that need to go into the different slots. The pattern matching engine is then capable of extracting the relevant attributes from a binary operator node and assign them to the 3 slots of the pattern below. The second approach is to have an active function, which is a static method of binop class in that case. This match method accepts a subject S and then again either returns a tuple that allows assigning one of the elements to one of the slots in the pattern, or it returns a marker that this fails. In this example here, the match function first checks whether the subject is an actual binop node, and if so, it extracts the 3 relevant attributes left, up and right and returns them as a tuple. In the second case, it checks whether we have a unary operator node and decides that it might be able to represent that still as a binary operator node on the basis that -x can be written as 0 minus x. In reality, we might not really want to do this particular thing here, but I hope it conveys the idea and in particular the power and versatility of such an active mapping or active pattern matching. If we return to the second view of pattern matching, where we say that a pattern is a constructor for a tree structure and we want to have this to yield an object that's equal to the given subject, we find that this is no longer appropriate because the subject on the right might actually have a much richer structure than we can express by the template or pattern on the left hand side. So the subject might have additional fields and attributes, particularly hidden ones that can never really be fully accounted for by the pattern on the left. This means that if we return to our objective of pattern matching, we have to modify it and introduce the projection pi. So given a pattern P with variables x, y and so on, a projection pi and the subject find a substitution that assigns a value to each of the variables in the pattern, such that if we replace the variables in the pattern by their respective values, we get something that's equal to the projection of our subject, rather than the subject itself. So the subject can actually be any kind of complicated object, and the projection is then responsible for extracting those fields and attributes that are of interest to us. And this is of course part of the pattern itself. There's one last step that we can take to make the active patterns even more powerful and versatile, and that is by allowing them to have an additional parameter. This is similar to a constructor, say, where usually you would think of a constructor of an object taking on data that should somehow end up in the object. However, it might have additional parameters that tell it how to interpret the data otherwise provided. A string constructor, for instance, might take a stream of bytes, but also an encoding that tells it how to interpret those bytes. In our case, we might decide to move the star operator node to be a parameter to binop, like so. Now, the binop mapping can now actively decide whether the given subject is a multiplication in some way. Think, for instance, of the case where the multiplication or product is represented by a subclass of binop, which is specialized, or it might use different symbols than the star to represent the multiplication internally. In Python code, we would write this using square brackets, and the star in this case would then be handed on to this match method as an additional parameter. It's now the burden of this match method to decide whether the subject fulfills this additional constraint. To summarize, pattern matching is a tool to filter and extract data from tree-like structures. Another way of looking at pattern matching is as understanding it as solving an equation where on the left-hand side we have a pattern with variables and on the right-hand side we have a subject. However, If we allow the subject on the right-hand side to be a fully fledged object, we have to account for the fact that this subject has a much richer structure than the pattern on the left-hand side could possibly express. We therefore introduce a projection π, which can be done in one of several ways. We could explicitly label the different slots in the pattern with the names of the attributes of the subject that it should be paired with. We could also add a passive mapping. That's a tuple of names of attributes that are then extracted from S and paired to the different elements in the pattern. Or we could introduce an active mapping. That's really a function that takes on the subject and returns a tuple of values that are then used to compare to the patterns. This active mapping can also be parametrized, giving rise to a very powerful and versatile feature. Finally, after a long and intense discussion with the Python community, we put together a Python enhancement proposal with the basic and core elements of pattern matching to be integrated and implemented in the upcoming Python 3.10. We are quite confident that pattern matching would make a very valuable and great feature and addition to Python. Thank you.